Good afternoon, everyone. My name is Rodrigo Antunes. I'm here with my colleagues Martin Aguiar and Luan Lang. We are researchers from University of Beira Interior in Portugal, and right now we are working with soft robotics, soft creepers, and what we brought you today is integrating conductive TPU in a self-sensing soft creeper. So, this work is integrated in the Robotics Sudway project. This project, as the name says, Sudway, involves Portugal, Spain, and France, and we are looking to develop 3 different areas. The meat cutting area, in which we will put a collaborative robot assisting the butcher in the meat cutting task. Then we have another area in toy assembly. Basically, we will have a collaborative robot assembling dolls. And finally, the area that we are responsible to develop, that is fruit manipulation. So, basically, we will have the fruit conveyor, and we have to select based in the company's parameters. Since as size, defects, any aspects are all that the company needs to separate. At our left, we have a quick demonstration, a static demonstration, in which we detect the fruit and we separate. But what I want to showcase here is the soft gripping part. As you can see, the gripper adapts to the shape of the object. Here is more work that we have done in the past months regarding the computational vision system. We already are acquiring some high-quality image in pitch detection, and now we are moving to phase 2, in which we developed a better AI vision system. But I'm here to present soft creepers, so I will talk about soft creepers. Sorry, here. What do we need? We need to handle fragile fruits, fragile objects as fruits. So we need precise and adaptive tools, and soft robotics has emerged in this type of applications. And we also have another challenge, that is the current solutions on the market are usually too expensive or not suitable for this type of companies, small and medium enterprises. So we want to develop a soft creeper made of TPU by additive manufacturing. So the objective is quite clear. We need to design and build a soft creeper capable of sensing deformation. We will explore TPU's behavior in soft robotic applications, and of course we will use cost-effective materials and methods accessible to smart, medium enterprises. So here we have like a small flow of the development process. So we started with an initial design with TPU, then we brought the Filaflex conductive filament by Recreus, and starting to improving the reliability with copper electrodes. I will explain next. And after that, we implement a force resistor sensor to establish some correlations between the measured resistance in the gripper and the real force applied at the object, and then build a demonstrator to brought you real data live today. So we started our analysis with some design concepts, but the one that really stood up was the fin-ray effect design, because there's no need of external sensors or actuators. Just the whole design embraces the object as force is applied, as we can see in this video. And another advantage is that fin-ray effect soft robotic fingers can be easily produced by additive manufacturing. And of course, we are trying to develop low-cost solutions. So this is an approach that is interesting for us. So, sorry, too much? Yeah. So the initial design, we inspired in the Festo DHIS original design. Then we changed a little bit the thickness of the contact side and the rear side. So we have a thinner contact side and a thicker rear side. We made some few alterations in the crossbeams. As you can see, there are a lot of variables that we can mix and mess up a little bit. So we already had some previous work in this aspect. And then there is like a printed version of the soft robotic finger. After that, we tried the conductive filament. So we printed the whole finger with conductive filament, and we tried to apply some force with different objects. We have like in this video, we have two crocodiles into a multimeter, and we can see the piezo-resistive behavior with the gripper deformation. But how can we ensure reliable contact surface points for resistance measurement? And so we start to develop a different design. We changed the base design of the finger, and we added two copper electrodes in it. So we have two different points. We can measure the resistance difference, and then we use a PTG structure to secure the soft robotic fingers and the copper electrodes. And then we fix them. The video is not working on the left. I can show. Oh, okay. So when we are squeezing the object, we can see some variation on the graph. We use the OR3E. This was the first setup, a little bit confused and not well organized, but we improved. After this, we needed, like, okay, we already have a variation of the value read by our microcontroller, but we need to establish a connection between that variation and the force made in the object. So we use the force resistor sensor. Once again, a voltage divider allows it to measure the analog values of the sensor. Then the UR3E was used to move sequentially the finger, pressing the sensor and the object in different checkpoints, like 0 grams, 50 grams, 100 grams, until we reach the 2 kilogram mark. At each checkpoint, the Arduino recorded the analog values corresponding to the applied force, and then that enabled to create a correlation. And so we registered every point, and we reached a fifth grade polynomial equation that established the correlation between the analog read and the force applied by the finger. As we can see, this equation is only valid to values superior than 250, because above that the force value is just too low. The sensor limit is between 0.2 Newton and 20 Newton. Regarding the experimental setup, we then installed the copper electrodes in the finger. We put the force resistor sensor in the object in the middle of the fingers, and then we start squeezing and releasing the object, like a cycling test. And the results here are quite promising, because the resistance of the finger is variating very concise, I think this is a very interesting experiment, and the tests were quite promising, as I said. And the force applied is also very concise. As we can see in the bottom of the resistance graph, we have like some variation at the end that probably happened due to some slippery, like the object started slipper a little bit. And the same can be registered in the force measured. So this really established a good correlation between both of the curves. So as we squeeze the object, the resistor drops. Finally, I couldn't bring the UR3 here to show you all the work, but we decided to build a portable device. So we switched the Arduino by an ESP32, so we could send the data to the computer by Bluetooth. We replaced the original batteries for one single battery and introduced the switch. So I will turn this on and show you. Oh, I don't think you can see it. Well, some technical problems. Murphy's Law. I think I might need some help. Okay, I'm not able to show it there, sorry. A little bit of improvisation, but if we squeeze, we can see the variation of the finger. I don't know if anyone can see it, sorry. And if I try to squeeze, the force will increase, and then I will start to decrease the force, and we can see the variation. Of course, we will improve the data filter, so it's more reliable, but I think this is very promising already, and the variation is quite clear. So, conclusions. We developed an affordable self-sensing soft gripper. We demonstrated that this idea is actually possible. We can sensorize soft grippers with conductive filament, and we want to continue our work. We delivered a compact and portable demonstration here. Not so well as I thought, but yeah, it worked. And we created what I believe is an accessible solution for small and medium enterprises, leveraging low-cost materials and additive manufacturing. And, well, we have just opened a new world with potential applications in the medical field, agriculture, and manufacturing at all. Regarding future work, we want to establish partnerships with filament producer companies, explore additional materials, multi-material printing. For example, we can try like different hardness material, but also conductive, or even try an hybrid solution with non-conductive filament and conductive filament that could allow the a better variation of the read value. We need to improve sensing resolution by optimizing the sensor design and use load cells on future tests, so we can have like a enhanced force calibration. Well, of course, the last one includes a wider variety of objects and real-world applications, such as industrial, agriculture, etc. I need to thanks the Robotics Software project, because allowed us to develop this technology and to bring it here today to present to you. I hope you like it. I thank you your attention. If you want to do any question or play around with the soft robotic finger, feel free to ask. Thank you very much.
Thank you very much. Are there any particular types of application that you're looking for? Obviously in agriculture and food, are there any particular types of objects basically that you're interested in working with?
We want to test it on fruits. That is the main object of the project. But I mean, as I said, we can test in every object, every small object or even larger object. We can produce a larger finger with different actuators, because this is also, we can use mechanical actuator, a simple mechanical actuator, an electric actuator, or even a pneumatic actuator. So the field is so open right now.
And in terms of multi-material printing, what really excites you about that? How do you think that will help the development?
If you have opportunity tomorrow, my colleague will also present sensors that we developed with with the conductive filament as frost detection sensors.
Okay.
And temperature sensors, also I don't remember the name right now, like a joystick, a game command with several buttons, also produced with the conductive filament, and we will also show that tomorrow. So that's an example of what this conductive filament can bring to the several areas.
Okay, perfect. We'll be back tomorrow then.
Thank you very much.
Thank you very much again.